All right, so a little bit more about the Bohr model in this video. Unfortunately for Niels Bohr, the boring world of Niels Bohr, right? No, actually, it's pretty interesting. Um, but it's sort of amazing to me how bad this model is, and yet we still teach it in chemistry curriculum across the country. But that's kind of the way it is, and you gotta know it. So but something that is interesting is that it basically only works for one electron systems, okay? And the reason is because it doesn't take into account electron-electron repulsion, okay? But it does illustrate nicely the principles that, energy is quantized. So I think this is why we still teach it, okay? So it only works for hydrogen. It'll work for a helium cation that has 2 protons, right, and 1 electron if it's He+, or a lithium 2+, that's 3 protons and a 1 proton. But it doesn't explain why the electrons surround the nucleus at various distances. And like I said, it doesn't take into account electron-electron repulsion, which is really important. The whole notion that there are orbits like this orbiting around the sun, it turns out to be completely false, okay? It's not like a solar system, guys. The atoms are not like solar systems, okay? It's really more complicated like that, unfortunately. And what we're going to try to do in the rest of this chapter is explain to you a better approximation of what it is. It's complicated math, but we're going to break it down into pictures eventually. And it has to do with electrons being like waves. So you can think about this as like a standing wave. So what does a standing wave mean? Imagine you have 2 people holding a jump rope, right? And then you swap the, maybe I would have done this in class. If we're in class, we'd hold a jump rope and you get a wave in there. Even though I'm not moving the jump rope left to right, the jump rope would make a wave. That's like what we call a standing wave, okay? So you can think about this as like a standing wave that's moving around the nucleus. So it's not a circular orbit. It's much more complicated than that. It's a wave-like thing combined with some circular movement. And it turns out there's some uncertainty actually what the path is. We'll talk about that probably in the next video too. And you're going to have constructive interference and destructive interference if you have more than one electron talking to one another, right? So this makes the whole thing pretty complicated when you're talking about quantum mechanics of the atom. And so deBroglie, a guy named deBroglie, scientist named deBroglie, really honed in this wave-particle duality, not just of light, but of matter. It turns out all matter is like light in that there's a wave-particle duality. All matter behaves partially like a wave and partially like a particle. Not even that. It's simultaneously, that's why we use the word duality. Simultaneously, it's behaving like a wave and a particle. It's crazy stuff to wrap your head around. Somebody named Heisenberg came up with what's called the uncertainty principle, and we'll go over that. It's another crazy thing of quantum mechanics. A lot of this stuff is pretty in-depth physics, explains a lot of the math behind it. We'll be able to understand the basic concepts, but I think whether or not you learn it in this course or you take the crazy physics courses, it's equally mind-blowing, really. The ramifications and the results. The universe is crazy, guys. I mean, it's just, there's some crazy things, and I think technology could really someday harness some of these crazy properties. For example, maybe you've heard of quantum computing, where you can get processing speeds way higher than anything currently possible. There's some pretty crazy things. And Schrodinger came up with the solutions to basically how these different waves of the electrons were interacting. And this is called a wave function. So he did all the gnarly math for us. And we'll look at his beautiful pictures that his math comes out. But so these are some people that did some of this work. And so we'll be going over these concepts. So is light a wave? Is light a particle? Mentioned this in the last video. No, it's both, okay? All matter acts as both a particle and wave, not just light. That's the crazy thing. And so deBroglie came up with this idea and quantified this using this equation here. Again, this is an equation on your formula sheets. where the mass is equal to, of your particle is equal to Planck's constant over its wavelength. It's always going to have a wavelength now, times by its velocity or speed. And just a real note here, this is not new, okay? This is not frequency, this is speed, velocity. So don't get confused on that, and make sure that you get that right. So let's go through this problem here. This is looking at somebody throwing a baseball, okay, at a certain speed. And to be nice, I converted that speed in miles per hour to meters per second, which is what we're going to need. What is the wavelength, the de Broglie wavelength of the baseball in nanometers? All matter has a wavelength. That's a crazy thing, okay? So let's see. When you throw a baseball, do you see a wave? No. It looks like it's traveling in roughly a straight line, unless you're, you know, throwing a gnarly curveball, right? But it's basically the curveball has to do with spin, okay? Not have to do with de Broglie's wavelength. Let's calculate de Broglie wavelength. So what did I do? I solved for lambda on that previous equation right here. So I just rearranged this, multiplied lambda up, and then divide the mass. Okay, so that comes lambda equals h over mv. Planck's constant is h. We know what that is, 6.626 times 10 to the minus 34 joule seconds. Okay. I'm showing you what a joule is here, reminding you it's a kilogram meter squared per second squared. If you don't remember that, you can always use the fact that kinetic energy is 1/2 mv squared and back it out like that. We did that in class earlier in the month. Okay. There it is. It's telling you joule, what a joule is in terms of units. And then we have the grams. I had to convert that to kilograms to get the kilograms and the joules to cancel, and the meters per second. And your final answer ends up being 1.08 times 10 to the minus 34 meters. That's small, guys. That's a damn small wavelength, okay? And if you convert that to nanometers, it's still really, really small, 10 to the minus 25. And so, you know, that's way smaller than an atom. That's way smaller than any subatomic particle. You're never going to be, in fact, quantum mechanics tells us, okay, which we'll see in the next video. Quantum mechanics tells us you're never going to be able to design any piece of scientific equipment that could ever detect such a small wavelength. So quantum mechanics tells us that a baseball does have its own unique wavelength, and that it's 1.08 times 10 to the minus 25 nanometers. But guess what? You're going to have to actually just use faith to actually prove that, okay? The only reason why we think this is true is because for other particles with much lower masses, if you have lower mass here, what happens to wavelength? It's in the denominator. It's like an electron, okay? Electron is going to have a measurable wavelength, definitely measurable, much bigger wavelength relatively, right? Because it has a smaller mass. So those you can detect, okay? Wavelength of a baseball, wavelength of us, wavelength of the Earth, no way you're going to detect. The mass is too big. All right, so that's basically very interesting ramification of quantum mechanics. Everything is like a wave. Everything is like a particle. Everything is both a particle and a wave at the same time.